researcher in Virginia did. This is the interactions of matter and radiation in the first 10 million years of the universe, shrunk to 10 seconds and raised from a deep organ pitch of a large universe, infant large universe, to audible range. So it was boosted by 50 octaves, and this is what the Big Bang actually sounded like. You didn't think I was going to show you the Big Bang. Actually, I'm going to, if we bring the sound up, I'll do that again, because that wasn't quite loud enough to hear. I'm going to rewind a little. So that's a sonification of the actual physical interactions of the first 10 million years of the universe, shrunk to 10 seconds and boosted by 50 octaves. And so now we can look at the known universe all the way out from the roof of the world to the dawn of time. So let's go back as early as we can, and now I'm moving into the part where we're not so sure. The things I've told you so far are pretty conventional cosmology. They've been established, actually in some cases, for a few decades with better and better evidence and data. And for people who work on the very, very early universe, theorists, not like myself, I use telescopes, actually what happens after the Big Bang is kind of dull, like they don't really care. We're looking back to the dawn of time now, even maybe before the Dark Ages if possible. An enormous success of the Big Bang model that's not as well publicized as the microwave background is the fact that we have physics that's tested in the first 3 minutes after the Big Bang. So a 13.7 billion-year-old universe, we have solidly tested astrophysics. Because the amount of helium in the universe, remember the universe mostly hydrogen and helium, is too much to have been produced by normal processes in those 100,000 billion stars. We understand stars very well. There is not enough helium made in all those stars to make 1/4 of the mass of the universe helium. However, the entire universe, 3 minutes after the Big Bang, was the temperature of the center of the sun. And like the sun, it made helium and other light elements. It didn't do it for long because it was expanding. The sun is stable. And in fact, not only helium, but 3 other light elements have their abundances measured in space. And their abundances of 4 different light element species match a single parameter, a single quantity in the Big Bang model, which is the density of order of matter, that 4% slice in the pie of the cosmic pie. This is a stunning success of the Big Bang model, because otherwise you have to explain where these light elements came from, and there's no other mechanism to explain them. But the Big Bang brilliantly explains something that happened in the first few minutes. That's our largest look-back time where we have a benchmark in very understood physics. However, we can trace the expansion all the way back. On a logarithmic plot, you can see going to crazy small fractions of a second, and there are theorists who are quite happy to explore the first fractions of a second, and next week you're going to enter the realm here. You're going to enter this realm. If you ask, where's our tether, our last tether on the world of the real, on the world of the lab, it's here. That's the limit of the Large Hadron Collider, which for an instant, under very special circumstances, can create this incredible temperature of tens of trillions of degrees, 10 trillion degrees, which corresponds to the Big Bang about a nanosecond after it happened. So lab physics can corroborate the Big Bang all the way back to here. Beyond here or before here, demons lurk. And Mike Turner will tell you all about those demons next week. It'll be fun. And I don't do that. I'm not a theorist. So when I try and think about the singularity, my head just hurts, or it explodes, or something happens. So let me just finish with the frontiers of the subject, which is sort of a taster of what Mike's going to talk about, because he's going to give full play to dark energy, to dark matter, to inflation, something I'm barely going to mention, and talk about where the limit of our knowledge is, because it's still an exciting subject. It's not like everything is written in the textbook. When you get to the first fraction of a second, you recognize unity in nature, symbolized by the Ouroboros, an ancient symbol found in almost all human cultures, the snake that eats its tail. And it represents the fact that over these 45 orders of magnitude of scale, our best place to test the fundamental theories of nature, of particles and atoms, at the very high temperatures, is the Big Bang itself. No better, no other. And we can zoom over those 45 orders of magnitude from the largest structures we see into the universe to the quarks at the heart of an atom, here done 2 seconds for every power of 10. And it is, in fact, the case, if you trace this story back, there is a fraction of time when the universe was smaller than an atom. And you have to understand it using the same physical theories we use to understand the interior of an atom. And there are still mysteries in that world, because, as you know, there are 4 forces of nature. As you go back in time towards the Big Bang, you simulate conditions of extraordinary temperature where these forces become indistinguishable. They merge together. And in fact, we are looking for a unified theory of nature that deals with a superforce that melts all of these forces together. At the moment, our physics is only tested to the merger of electromagnetism and weak, with hints of what goes on before, because we can't do better in the lab. In the Big Bang, we have witnessed, or we could witness, the superforce in operation. And I'll give a taste again of things that Mike should talk about more next week, but the reason why there are a billion photons or several billion photons for every particle, is that a tiny imbalance in the forces of nature early on left us with, say, 10 billion and 1 particles for every 10 billion antiparticles, and they all annihilated, leaving you with a residue of matter. So the billion photons we see cooled into microwaves represent the totality of radiation from this matter-antimatter annihilation, and the little residue went on to become 100 billion galaxies. This must have been an amazing thing to witness. Another thing that I'm glad I wasn't around, actually. Another thing that Mike will talk about next week is something called inflation. It's a hypothetical era, very early, look at the crazy small number, 10 to the minus 35 seconds, when the universe inflated from many times smaller than a proton to about the size of a tennis ball. That's a nice, familiar object, a tennis ball. We can imagine the universe as a tennis ball. And we use inflation. It's motivated by this merger of forces as a mechanism, but we use inflation to explain why the universe is so smooth and flat, which otherwise is not a feature of the standard Big Bang. It's not explained naturally in the Big Bang model. What we're really reaching for is a theory of everything that incorporates gravity. Now, you know this, everyone's entitled to their own theory of everything. It's fine. There can be 1,000 theories of everything. Let 1,000 flowers bloom. Now, you probably know that Einstein fruitlessly spent the last 15 years of his career searching for a unified theory that incorporated gravity. It's a very hard thing to do. The current frontier theory, which I will just skate over very briefly, it's beyond my domain here, and you will hear more about it next week, is string theory, which postulates another deeper level of structure beyond the electrons, protons, neutrons, and quarks that we're familiar with in our standard model of physics. So these are extraordinary ideas that postulate tiny one-dimensional entities, vastly smaller than a proton, which compose everything there is. And they're motivated by extremely beautiful but extremely difficult mathematics. These theories of nature only work when there are about 10 or 11 space-time dimensions. And the mathematics, of course, is very difficult. This has not been observed. It's extremely hypothetical theorizing that's reaching for another level of structure. If it's relevant at all, though, it must be relevant to the early universe, as well as to what matter is made of. And so we actually are faced with the probability, to use the word that's relevant, that the universe is a quantum entity.
It upset Einstein very much, you know. All that damned quantum jumping. It spoiled his idea of God, which I tell you frankly is the only idea of Einstein's I never understood. He believed in the same God as Newton, causality, nothing without a reason, but now one thing led to another until causality was dead. Quantum mechanics made everything, finally, random. A thing could be this way or that way. The mathematics deny certainty, they reveal only probability and chance. And Einstein couldn't believe in a God who threw dice. He should have come to me. I would have told him. Listen, Albert, he threw you. Look around. He never stopped.
Well, you've been a good audience and you've come this far, so one last little turn in the roller coaster that hopefully doesn't eject you at a high speed and a high height. I'll talk about the multiverse, which is a frontier idea based on the idea of the universe as a quantum originating event, which logically leads to the possibility of other quantum events. In the inflationary idea, which you will definitely hear more about if you go next week, that's Mike Turner's specialty, one of his specialties, inflation, this early epoch of very rapid expansion from microscopic scales to the beginning of a macroscopic scale, actually stretched quantum fluctuations into ripples that became the seeds for galaxies to form. So in that microwave map of the sky with the red, yellow, and blue colors, those little speckles that are about a degree across in the sky, if inflation is correct, those speckles are quantum fluctuations boosted to the size of galaxies that would subsequently evolve into systems of hundreds of billions of stars. Quite a wild idea, isn't it? And it's the basis for the idea of parallel universes, because if you have a set of quantum fluctuations originating at the origin of time and space, then you have a mechanism where our inflating bubble of space-time is not the only one. There can be many. And because of the random nature of quantum fluctuations, those parallel universes, if you like, will be randomly different in their properties. They won't all be like this one. How do we understand these randomly different universes? Well, we reach for string theory, and string theory doesn't help very much because it's too difficult to calculate in. But the best string theorists will tell you is that there are 10 to the power 500 different possible vacuum states in string theory. And so that